Atom transfer radical polymerization, ATRP, is a type of controlled or living radical polymerization that allows for precise control over molecular weight, architecture, and composition of polymers. It was first developed in the mid-1990s by Krzysztof Matyjaszewski and Jianhui at Carnegie Mellon University. For over 25 years, ATRP has been used to make polymers with predetermined molecular weight, low dispersity, functionality, and architecture. A TRP has experienced an incessant evolution in terms of catalyst and reaction design, becoming one of the most prominent examples of catalysis in polymer chemistry. From a mechanistic point of view, ATRP is rooted in atom transfer radical addition, ATRA, and inspired by metal-catalyzed telomerizations and redox-initiated polymerizations. In contrast to telomerizations, where polymer MW does not increase with monomer conversion, in a typical ATRP, the polymer molecular weight increases linearly with conversion, retaining low dispersity and indicating that all chains grow concurrently. A TRP kinetics follow the principle of the persistent radical effect, PRE. According to the PRE, if a system can generate both a persistent, stable radical and a transient radical at an equal rate, the latter is involved in self-termination events that trigger the buildup of the persistent radical concentration. This guides the system toward cross-termination between persistent and transient radicals, minimizing the self-termination of transient unstable species. In ATRP, the persistent radical is an oxidized metal catalyst termed the deactivator, while the corresponding reduced metal catalyst is the activator. The concept of activation-deactivation that is at the core of ATRP derives from ATRA. Transition metal-catalyzed ATRA was developed in the 1960s to add an alkyl halide across a carbon-carbon double bond. Copper complexes are the most common ATRA catalysts. The mechanism of copper-catalyzed ATRA involves the halogen atom abstraction from an alkyl halide RX substrate by a copper-1 ligand complex. ATRP is based on a similar mechanism of radical activation/deactivation as that of ATRA. However, the macroradicals generated upon the addition of monomer molecules are susceptible to further activation. Basic principle: a TRP is based on a reversible redox process between an active radical species and a dormant halogen-capped polymer chain, mediated by a transition metal catalyst, typically copper. Mechanism: steps. Initiation. The alkyl halide reacts with the copper-1 ligand complex to form an alkyl radical and copper-2 halide complex. Propagation. The radical adds to monomers to grow the polymer chain. Reversible deactivation. The growing radical reacts with copper-2 halide ligand complex to reform the dormant halogen-terminated chain. The equilibrium between active and dormant species ensures that the concentration of radicals is low, which minimizes termination and allows for controlled growth. Features and advantages: controlled molecular weight with narrow dispersity, 1.1 to 1.3. Predictable architecture: block, graft, star, brush polymers. Wide monomer compatibility. Functional chain ends for post-polymerization modification. Mild conditions and tolerance to impurities, especially in aqueous ATRP. Finally, the development of new catalysts and systems to trigger ATRP under mild, non-toxic conditions, coupled with the continuous study of polymerization mechanisms, offers the opportunity to design polymer and inorganic/polymer hybrid materials with precisely controlled features for a broad variety of applications. These includes super soft materials, bioconjugates, and polymeric carriers for drug delivery, and functionalized surfaces with lubricious, antimicrobial, or antifouling properties. As researchers continuously address these challenges and exploit these opportunities, ATRP will continue to be a valuable strategy for the synthesis of functional polymer materials for advanced technological applications. Moreover, atom transfer radical reactions for small molecule transformations can also benefit from present and future advances in ATRP.